Download this code from codegive.com, link in the description below. OK, let's dive into BCD, binary coded decimal, counters and finite state machines, FSMs, with practical code examples. This will be a comprehensive guide, covering the theoretical background, design principles, and implementation using hardware description languages, HDLs, like Verilog. Part 1, BCD counters. 1.1 Understanding BCD representation. What is BCD? Binary coded decimal, BCD, is a way to represent decimal digits, 0 through 9, using binary code. Instead of directly converting a decimal number to its binary equivalent, each decimal digit is represented by its own 4-bit binary value. Why use BCD? BCD is particularly useful in applications where you need to display decimal numbers or interface with decimal-based systems. Direct binary to decimal conversion can be complex. BCD simplifies this, especially when dealing with human-readable output. Calculators, digital clocks, and some industrial control systems often employ BCD. BCD encoding. The most common BCD encoding is 8421 BCD. This means the 4 bits represent the decimal value using the weights 8, 4, 2, and 1 respectively. Decimal BCD, 8421. Dash 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 dash. 00000. 10001. 20010, 30011, 40100, 50101, 60110, 70111, 81000, 91001. Important note: the BCD representation only uses the binary codes 0000 to 1001. The binary codes 1010, 10, through 1111, 15, are invalid in BCD. 1.2 BCD counter design. A BCD counter counts from 0 to 9 and then resets to 0, instead of counting all the way to 15, 1111 in binary. Here's the basic logic. 1 increment *, the counter increments its 4-bit BCD value on each clock pulse. To detect 10, 1010, we need to detect when the counter reaches the decimal value of 10, 1010 in binary. Since BCD doesn't use 10 to 15, we reset the counter. 3 Reset * when 10 is detected, the counter is reset to 0, 0000. 1.3 Verilog implementation of a BCD counter. Explanation **** module BCD_counter, defines the module name. Input CLK, reset, inputs, clock and reset signals. Output reg3:0 count, output, 4-bit BCD count value, declared as reg because it's assigned within an always block. Output reg carry_out, output, carry out signal to chain BCD counters together. Always at, posage CLK or posage reset, this is a clocked always block. The code inside executes on the rising edge of the CLK signal or when the reset signal is high, asynchronous reset. If, reset, asynchronous reset condition. If reset is asserted, the counter is set to 0. Else begin, and, if reset is not asserted, the counter proceeds with normal operation. If, count equals 4B1001, checks if the count is equal to 9, 1001 in BCD. If so, the counter is reset to 0 and the carry_out is set to 1. Asterisk else count equals count plus 1 b1, if the count is not 9, it's incremented. Asterisk carry underscore out equals 0, if the count isn't 9, carry underscore out is 0. 1.4 Cascading BCD counters, creating multi-digit counters. To create a multi-digit BCD counter, example a counter that counts from 00 to 99, you can cascade individual BCD counters. The carry underscore out of one counter becomes the clock enable for the next counter. Explanation asterisk. Asterisk BCD underscore counter underscore top level module connecting two BCD counters. Asterisk digit 1, digit 2, output digits, least significant and most significant. Asterisk carry 1, internal wire to connect the carry underscore out of the first counter to the second counter's clock enable logic. Asterisk counter 1, instantiation of the BCD underscore counter module, the first digit. Asterisk the always block handling digit 2 increments only when carry 1 is asserted. Simulation and verification. It's crucial to simulate your BCD counter design to verify its functionality. You can use a test bench in Verilog to drive the clock and reset signals and observe the output. Tools like Model Sim, Vivado Simulator, or Icarus Verilog can be used for simulation. Part 2, Finite State Machines, FSMs. 2.1 Understanding Finite State Machines. Asterisk what is an FSM? A finite state machine, FSM, is a mathematical model of computation used to design sequential logic circuits. It consists of a finite number of states and transitions between those states based on input signals. Asterisk key components asterisk. Asterisk states asterisk the different conditions or modes the system can be in. Asterisk inputs asterisk signals that trigger transitions between states. Asterisk outputs asterisk signals generated based on the current state and, sometimes, the input. Asterisk transitions asterisk rules that determine how the FSM moves from one state to another based on the input. Asterisk types of FSMs asterisk. Asterisk Moore machine asterisk the output depends only on the current state. Asterisk Mealy machine asterisk the output depends on both the current state and the input. Asterisk state diagrams asterisk FSMs are often represented visually using state diagrams. States are drawn as circles or ovals, and transitions are drawn as arrows labeled with the input conditions that cause the transition. Outputs, if Moore style, are listed inside the state circle. 2.2 FSM Design Process. 1. Define the problem asterisk clearly understand the behavior you want the FSM to implement. Determine the inputs, outputs, and states. 2. Create a state diagram asterisk draw a state diagram representing the FSM. This is crucial for visualizing the behavior. 3. Create a state table asterisk the state table is a tabular representation of the state diagram. It lists the current state, the input conditions, the next state, and the output. 4. State encoding asterisk assign binary codes to each state. This is necessary for implementation in digital circuits. The number of flip-flops needed is determined by the number of states, number underscore of underscore flip-flops equals seal, log 2, number underscore of underscore states. 5. Implement the FSM in HDL asterisk write Verilog, or VHDL, code based on the state table and state encoding. 2.3 Verilog implementation of an FSM, Moore machine example. Let's design a simple sequence detector that detects the sequence 101 in a serial input stream. We'll use a Moore machine. 1. Define the problem asterisk. Asterisk input, serial underscore in, 1-bit serial input. Asterisk output, sequence underscore detected, 1 if the sequence 101 is detected, 0 otherwise. Asterisk states. Asterisk s underscore idle, initial state, waiting for a 1. Asterisk s underscore 1, received a 1. Asterisk s underscore 1 underscore 0, received 10. Asterisk s underscore 1 underscore 0 underscore 1, received 101, sequence detected. 2 state diagram asterisk. 3 state table asterisk. Current state serial underscore in next state sequence underscore detected. Dash 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 dash. S underscore idle 0 S underscore idle 0. S underscore idle 1 S underscore 1 0. S underscore 1 0 S underscore 1 underscore 0 0. S underscore 1 1 S underscore 1 0. S underscore 1 underscore 0 0 S underscore idle 0. S underscore 1 underscore 0 1 S underscore 1 underscore 0 underscore 1 0. S underscore 1 underscore 0 underscore 1 0 S underscore idle 1. S underscore 1 underscore 0 underscore 1 1 S underscore 1 1. 4 state encoding asterisk. State encoding. Dash 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 dash. S underscore idle 0 0. S underscore 1 0 1. S underscore 1 underscore 0 10. S underscore 1 underscore 0 underscore 1 11. 5 verilog implementation asterisk. Explanation asterisk. Asterisk module sequence underscore detector, defines the module. Asterisk local param, defines symbolic names for the states, makes the code more readable. Asterisk reg 1:0 current underscore state, next underscore state, state registers. Current underscore state holds the current state, and next underscore state holds the next state calculated combinatorially. Asterisk always at, posage CLK or posage reset, synchronous state update. On each clock cycle, the current underscore state is updated to the next underscore state. Asterisk always at, asterisk, combinational logic to determine the next underscore state based on the current underscore state and the serial underscore in input. The case statement implements the state transitions described in the state table. Asterisk always at, current underscore state, combinational logic to determine the output, sequence underscore detected, based on the current underscore state. This is a Moore machine, so the output depends only on the state. 2.4 Mealy machine example, alternative implementation. We can also implement the sequence detector as a Mealy machine. The primary difference is that the output logic depends on both the current state and the input. Key differences in the Mealy machine implementation asterisk. Asterisk the sequence underscore detected output is determined within the always at, asterisk, block, alongside the next underscore state logic. This means the output changes combinatorially in response to both the current state and the input. Asterisk note that in the case of detecting 101, the output sequence underscore detected becomes 1 during the state transition from S underscore 1 underscore 0 when serial underscore in is 1. The Moore machine, in contrast, would assert the output in the next state, S underscore 1 underscore 0 underscore 1. 2.5 Simulation and verification of FSMs. As with BCD counters, thorough simulation is essential for FSMs. Create a test bench that applies various input sequences and verifies that the output behaves as expected. For example, in the sequence detector, you'd want to test cases where the sequence 101 occurs, doesn't occur, overlaps, and is interrupted. Test bench example for Moore FSM. Key takeaways. Asterisk BCD counters asterisk use BCD when you need to work directly with decimal digits. Understand the 8421 encoding and the logic for resetting at 10. Asterisk FSMs asterisk finite state machines are powerful for designing sequential logic. Learn to create state diagrams, state tables, and implement fsms in Verilog. Understand the difference between Moore and Mealy machines. Asterisk simulation is critical. Asterisk always simulate your designs thoroughly to catch errors and verify correct behavior. This detailed tutorial should provide you with a solid foundation in BCD counters and finite state machines. Remember to practice by building and simulating different examples to solidify your understanding. Good luck.